everyone, I'm J Wildberger. We're carrying on looking at the cyclotomic polynomials or polynumbers. And today we're going to be looking at logical difficulties associated with closely related algebraic objects called cyclotomic fields. And it's all around this idea of showing the irreducibility of the general cyclotomic polynumbers phi sub n, where n is a natural number 1, 2, or 3. Now, the Schoenmann-Eisenstein criterion that we talked about in our last video establishes that these guys are irreducible if the n is a prime p. However, it leaves the very important question, how do you prove that phi sub n is irreducible for a general natural number? Now, historically, a lot of people have looked at this. The first proof was given by Kronecker in 1854. Dedekind gave a proof in 1857. Schur and Landau in 1929 both gave proofs, which I think more or less were elaborations or simplifications of earlier proofs given by Mertens. Now, from our point of view, although I haven't looked at all of these proofs exhaustively, my feeling is that there is something fundamentally problematic about the logical structure of things, and it has all to do with the nature of the cyclotomic fields. And so we're going to be talking about some issues today that cut across field theory and modern Galois theory. So they actually have quite a lot to say about even undergraduate courses in these important subjects. So what is it that I object to with these classical proofs? It is that they all rely on complex numbers and identifying roots of unity within them using the Fundamental Theorem of Algebra. So the main objection is that really this is not algebra. Okay? We're going outside of algebra to analysis, where infinite processes are required to set up the complex numbers and actually also to obtain the roots of unity the way they're usually represented. So I want to emphasize that from my point of view, this makes these classical proofs logically invalid. And so that from my point of view, even though I haven't studied this intensively, there is some logical issues. There's some fundamental problems with the way we set up this theory. So we need to have another look. We have to go back. We have to understand what's going on here, sort of from a more deeper algebraic level. But let me at least outline the standard point of view towards this topic. So the usual idea is that to factor 1 minus alpha to the n, what we're going to first do is find the zeros of the equation 1 minus alpha to the n equals 0. That's a reasonable idea. That's the same as finding solutions to alpha to the n equals 1. Now there's one obvious solution, which is alpha equals 1. And if n is even, there's the other solution, alpha equals minus 1. But when you go to the complex domain, in quotes, then supposedly there are then n distinct solutions, because this is an equation of degree n, and the Fundamental Theorem of Algebra, which is not really a theorem, but it's believed, says that a polynomial equation of degree n ought to have n different, or maybe not different, but n solutions. So let's call these something. Let's call them, say, zeta 0, zeta 1, up to zeta to the n minus 1. I apologize, my zetas don't look exactly like zetas, but this is supposed to be a zeta. And with zeta 0, say, equaling 1. And then in terms of those, we could then perhaps hope to factor alpha to the n minus 1 as alpha minus 1, alpha minus zeta 1, alpha minus zeta 2, all the way up to alpha minus zeta to the n minus 1. In other words, if we have the zeros of this polynumber, then we can factor it into linear factors accordingly. So that's a starting point. But already that is highly problematic from my point of view. So let me illustrate the story with an explicit example when n is equal to 15, which is of independent interest. So it turns out that phi sub 15 is the polynumber 1 minus alpha plus alpha cubed minus alpha to the 4th plus alpha to the 5th minus alpha to the 7th plus alpha to the 8th. And when we had our list of the sort of simplest cyclotomic polynumbers, this was probably the most interesting one, the one that sort of sprung out at you as certainly not being obvious at all. And let's have a look at the associated geometry, which is the usual story, where we're using the complex numbers on the so-called unit circle in the complex plane. So this is supposed to be the complex plane with 1 and minus 1 here, and I here and minus I here, and this is x squared plus y squared equals 1. So then the 15th roots of unity are these 15 values that you see here, equally spaced around the unit circle. And if we call this, say, zeta 1, then this might maybe start with zeta 0. That would make more sense. So zeta 0 is 1. And then zeta 1 is this first one up here as we're sort of going up in the counterclockwise direction. There's zeta 2, zeta 3, zeta 4, zeta 5, zeta 6, zeta 7, zeta 8, zeta 9, zeta 10, zeta 11, zeta 12, zeta 13, and zeta 14. So 15 of them all together. So in the usual story, zeta 1 is described in terms of its argument. Okay, that's the angle made by this positive x-axis and this line that you get by joining the origin to zeta 1. And that is 2 pi on 15, which in the more sensible Babylonian system that's been around for thousands of years is 24 degrees, because that's 360 divided by 15. Now, for simplicity, let's call this zeta 1 just zeta. If we do that, then all the zetas can be described in terms of just zeta by the equation that zeta sub k is equal to zeta to the k, where we're using complex number multiplication. So if we take this is zeta, maybe I'll write that down just to clarify that. Okay, that's zeta. Then here is zeta squared, zeta cubed, zeta to the fourth, etc. Now, these 15 15th roots of unity have some different aspects. Some of them are a little bit different than others. And I want to draw your attention to the 3 here that are formed by this red triangle. Okay, so there's 1, and then there's zeta 5 and zeta 10. These are rather special because they are not only 15th roots of unity, they're also cubed roots of unity. In other words, they have the property that if you take one of these and you cube it, you're going to get 1. Similarly, the vertices of the green pentagon have some special properties. That's zeta 3, zeta 6, zeta 9, zeta 12, and of course zeta 0. They are all of order 5. Well, not zeta 0, but the other 4 are order 5, meaning that if you take zeta 3 and you raise it to the 5th power, then you get 1, but no lesser power. Okay? So the set of all 15th roots of unity are sort of separate into these sort of classes. So these ones here that are associated to the 3rd roots of unity, I guess we should start with this one here. This one here is special, obviously. And then there's the 3rd roots of unity. And then there's also the 5th roots of unity. And then there's the rest. And the rest have the property that the smallest power that you need to raise them to get back to 1 is 15. So for example, if we take zeta itself, you have to raise it actually to the 15th power to get back to zeta 0. Let me remind you that when you raise a power on the unit circle, what happens is that the sector that you're subtending is always augmenting by an equal amount. So in terms of angles, the angle is doubling and then tripling and then quadrupling and so on. Okay, so let's have a look at 1 minus alpha to the 15. We're trying to factor that. According to the standard theory, it's then going to be a product of all kinds of factors corresponding to each one of these nth roots of unity. So there's going to be 1 minus alpha corresponding to that, zeta 5 minus alpha corresponding to that, zeta 10 minus alpha corresponding to that, and then the 4 factors corresponding to these 4 things on the pentagon. Now what happens is because these two, zeta 5 and zeta 10, are cubed roots of unity, it means that when you multiply these 2 factors together, you get this quadratic factor, 1 plus alpha squared. That's exactly the cyclotomic polynomial phi sub 3. And when you multiply these four together, you get this fourth degree polynumber, which is exactly phi sub 5. And of course, this one here is phi sub 1. So our understanding is that the phi sub 15, which is what we're really interested in, which is this thing here, is going to be the additional factor that you get when you're factoring this into phi sub 1, phi sub 3, phi sub 5, and then the other one is phi sub 15. So continuing with that, we can conclude that phi sub 15 is going to be, in terms of these 15th roots of unity, zeta 1 minus alpha times zeta 2 minus alpha times zeta 4 minus alpha times zeta 7 minus alpha times zeta 8 minus alpha times zeta 11 minus alpha times zeta 13 minus alpha times zeta 14 minus alpha. And these indices here are exactly the indices which are relatively prime to 15. Don't share any factors. Okay, so now I can explain the rough idea of the classical proofs of the irreducibility of phi sub n. The basic idea is to start with this kind of factorization into these linear factors, and then to try to argue that you can't find some subset of these linear factors that together will, when you multiply them out, produce a polynomial, polynumber, with integer or rational coefficients. Okay, and the argument is something like this, that if f is a factor of this, say, phi sub n in general, then it means that f of zeta I is 0. It must contain one of these things at least, for some I with I and n relatively prime, just like in this case. So maybe it's going to have at least, say, one of these factors, maybe phi sub 13 minus alpha, might have some others. And then you try to prove that from that it must also be that f is a 0 on any prime power zeta sub I to the p for a prime p which is not dividing n. So for example, suppose that f had zeta 13 as a factor. Then we would want to show that if you, say, square zeta 13, because 2 is relatively prime to 15, that you're going to get another 0 of the same factor. And from that, you can basically deduce that all of these factors sort of have to be involved, because if you, by suitable squaring or raising to the fourth power and raising to powers which are relatively prime to this, you can show that you can get from one of these to any of the others. Okay, so that's the rough idea. So I claim that this logical framework doesn't actually really work. So what actually is the problem? Well, as often with these things, the problem is at the foundational level, about the assumptions that you're using to start out the argument. So the problem is to do with the definition and or the construction of the nth roots of unity in the first place. So this is really the same as wrestling with this so-called cyclotomic field. Q adjoin zeta sub n, where now zeta sub n refers to a primitive nth root of unity, where that means that zeta n actually has order n. Okay, so in algebra, this is a very important algebraic object. Okay, it plays a big role in algebraic number theory and in Galois theory, so it's a very interesting thing. But there are two very different ways of approaching it. Okay, two very different ways of approaching it. One is purely algebraic, let's call it method A. And the other one is not algebraic at all, it's highly analytic, let's call it method B. And to understand the difference between these two approaches is key to understanding the entire structure here. Okay. So with the first approach, you can construct the cyclotomic field algebraically. Now, this is a very interesting project, okay, and it does require some development of prior algebra. You need to establish some field theory first, and typically also some ring theory. And crucially, you need as an ingredient the irreducibility of the cyclotomic polynumber phi sub n. And I'm going to be showing you how this works in actually our next famous math problem, the one that's following this one. Okay, so we're going to come back to this algebraic way of trying to construct these cyclotomic extensions of the rationals. But it's to be contrasted with this other approach, which supposes that you can find this cyclotomic field. So this is a field that contains the rational numbers. That's what this sort of means. It's like a bigger field, has the rational numbers inside, and it's obtained by throwing in some extra things. And what are these extra things? Well, they are to be thought of as things found in the bigger field of complex numbers. So we go to this complex number domain, which is a vast extension of the rational numbers. Okay, it may not look like it because you have seen pictures of the complex numbers as a two-dimensional plane, you know, and there's sort of the horizontal, and you say that's the real number line, and then you take this extra dimension that has an I involved, as I've already shown you. But this is a huge jump from the rationals because implicitly here in the horizontal direction are the so-called real numbers. That's where all the complexity actually resides, in the real numbers as opposed to the rationals. So this is all touching base with this fundamental problem that we talked about in our last famous math problem, number 19, right? It's all having to do with the nature of the continuum. And this is really demonstrating this crucial aspect of this problem right here. So the story that's usually presented is that we're working in this quadratic extension of the real numbers, and there's the usual picture, and then we can find our primitive nth root of unity, okay, on the unit circle, and you just say something like, well, oh, look, there's a point. What point is that? It's the point with angle 2 pi on n. We just divide the circumference into n equal pieces, and then that's the first one. So there it is. There's zeta sub n, and then all the other ones are just powers of that. This is very, very problematic. Okay, seriously problematic, because implicit in all of this is that we've gone outside of algebra to analysis, where we've had to incorporate infinite processes to set up the entire arithmetic and actually the structure of the complex numbers in the first place. Okay, so this is no longer algebra. You may call it algebra. You may say, oh, this is the fundamental theorem of algebra, but it isn't. It's analysis. And if you look carefully at the analysis, there's actually topology involved there as well. So we're far from really doing algebra here. So to clarify the difficulties with really getting a hold of these nth roots of unity in general, let's have a look at the 9th roots of unity. The solutions of 1 minus alpha to the 9 equals 0, or the numbers in the complex plane which satisfy that alpha to the 9 equals 1. Here they are arranged uniformly along the unit circle. There is 1 zeta, zeta squared, zeta cubed, which is actually simpler. It's actually a cubed root of unity because it's at 120 degrees. And then there's zeta to the 4th, zeta to the 5th, zeta to the 6th. There's the other cubed root of unity, zeta to the 7, and zeta to the 8. When we look at 1 minus alpha to the 9, its decomposition into factors is phi sub 1, phi sub 3, phi sub 9. And here they are. There's phi sub 1, there's phi sub 3, there's phi sub 9. The phi sub 3 is the product of the two linear factors corresponding to these two zeros. This one, of course, corresponds to this one. So this last factor, the phi sub 9, corresponds to the other 6 zeros. Starting with, say, zeta, this one here, the primitive 9th root of unity, which we could express as cosine 2 pi on 9 plus I sine 2 pi on 9, if you believe the standard story, which I don't. Now, in terms of this zeta, which you can't actually get at, but we'll talk about that in a second. In terms of this thing, the cyclotomic polynumber phi sub 9 can be expressed as the product of these 6 linear factors, one for each one of these primitive 9th roots of unity. Now, while these ones here, the zeta cubed and the zeta the 6, are the cubed roots of unity, they are actually constructible by ruler and compass. But the other 6, in fact, are not. They are not constructible by ruler and compass. And so there's definitely a different aspect to them as to these ones here. So, but still, we could ask the question, how do you actually get a hold of such a thing? I mean, it all revolves around, you can see the arithmetic revolves around this primitive 9th root of unity. And how do you actually get your hands on this thing? How can you convince yourself that this thing actually, makes sense? Does it actually make sense? So it's very tempting to talk about mathematical objects even before they've been really completely defined and clarified. And that's what typically happens with this roots of unity story. We end up talking about these things as if they existed because we can kind of draw them on the unit circle in the complex plane. But when we actually ask, what is actually the definition of this thing? To get this zeta here, cosine 2 pi over 9 plus I sine 2 pi over 9, that's a complex number supposedly. There's a real part, there's an imaginary part. You have to actually be able to obtain these 2 real numbers first. So there's no getting around that a complex number is a pair of real numbers ultimately. And if you can't get the real numbers, then you don't have the complex numbers either, no matter what kind of notation you want to introduce. For example, you could write this as e to the I 2 pi on 9. Maybe that's psychologically, simpler somehow, but it still doesn't avoid the problem that you actually first have to find these real numbers. So how do you do that? Suppose you actually had to find cosine 2 pi on 9. In other words, let's say we're actually inquiring as to what it actually means. Okay, so there's pi according to the usual story. Pi is some infinite decimal that starts 3.14159, etc. It's known these days to about 5 or 10 trillion places, which is quite a lot. But nevertheless, even that huge decimal is just the beginnings of the real thing, which we're pretending is, existing outside of our universe somehow. So we write down something like this. We put down a string of digits, enough to convince us. We throw in 3 dots and say, okay, there's pi. We've got pi. It's a pretending because we don't actually have pi. Let's carry on. How do you then get 2 pi? Well, you have to multiply this thing by 2. That's an infinite amount of work. Let's pretend we can do that. Then you have to divide by 9. You can do that if it's a finite decimal, and you can sort of prescribe what you get. But with an infinite decimal, there's another infinite amount of work to be able to write down 2 pi on 9. So we just write something like this, the 3 dots, and then we pretend that we have it. At this point here, we've done the easy work, okay, and now we have to roll up our sleeves and get down to the serious business, which is calculating cosine of this thing. So you have to use something like cosine of x equals the series 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So you have to sub in for x this infinite decimal which you've obtained up here. You have to plug it in there. You have to calculate x squared, infinite amount of work. Divide by 2, infinite amount of work. Calculate x to the 4th, infinite amount of work, etc. Add them all up. Infinite amounts of work. And then you say, okay, now we do this and we get cosine of 2 pi on 9, which is something else like this. Of course, we don't really get this. This is just some kind of pretending, right? We're just pretending that we can do this arithmetic when we actually obviously can't do it. And we reconcile things by saying, oh, well, there's some indeterminacy there in the 3 dots. Okay. And then for the imaginary part, well, we have to play the same kind of almost empty game with sine x, and then we pretend that we can get sine x and we write down an expression like this. Our calculators are happy to give us decimals up to a certain point, and then we pretend that we've got the rest. So you see that there's a crucial fiction here. Okay? There's a crucial fiction in pretending that we write down an expression like this, that it actually is representing a well-defined object. It's not. Simply because there is quadrillions of decimals that we have not specified. Actually, not quadrillions, an infinite number of them. We've basically got nowhere. To a first approximation, we've got nowhere in specifying these things. The difficulty of constructing roots of unity inside the complex numbers is a manifestation and parallels the impossibility of trisecting a general angle, which was actually established by Wansel in 1837, even though the problem is one of the great problems of antiquity going back to ancient Greek times. So the problem is, if you have a circle and you have some sector of it, say between the axis there and the axis there, and you want to subdivide that into 3 equal sectors, how do you do it? Well, I've just eyeballed it, okay, and then you can sort of draw these things here and say, okay, that's what we're aiming for. We want these sectors to be equal. And this is, in general, not something that you can do with ruler and compass. And that was suspected by the ancient Greeks, but only proven in the 19th century. However, it's worth mentioning that it actually is possible to do that with origami and paper folding. Okay, but nevertheless, the problem is that this is only for a cubic kind of problem where you're subdividing an angle into 3. If you want to subdivide an angle into 5 or 7 or 37, well, it's even more complicated, okay? The bigger the prime that you want to subdivide something, the more difficult it actually is. So the whole idea of taking some sector and saying, okay, let's divide it by 37. Let's divide it into 37 equal parts. Okay? This is a dream that's not supported by our arithmetic. Okay? And it's a painful fact. And that's really another way of getting at what the real problem is with these roots of unity when we approach them from this complex number point of view. So in summary, the idea of finding a cyclotomic extension of the rational numbers given by an nth root of unity inside the complex numbers is a fairy tale, people. It's a fairy tale. It's a dream. It's something which is only approximately true and will never be more than just approximately true. Now, that's not to say that you can't create these things. You can certainly create these things, but you have to look in a different direction. You have to look in the pure algebra direction, and I'm going to be showing you how to do that in our next famous math problem. But we are still wanting to at least make some progress to the current famous math problem, which is how do you actually calculate these cyclotomic polynumbers. Even though maybe there's some dubious aspects about the underlying theory which need to be clarified and developed more properly. But still, practically speaking, if I want to calculate phi sub 1001, how do I best go about doing that? In my next video, I'll tell you some of the best techniques for doing that. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.